Hi everyone! Today we're going to focus on another problem application. I think that's the best way to learn these types of concepts. But now our production function is a little bit different. We're going to focus on a Cobb-Douglas production function with a rental price of $10 and a wage of $40. And we want, our constraint here is quantity to be 1,000. And our question is, what is the cost needed? That is the cost min problem. What is the cost needed to achieve that 1,000, and what is the amount of labor and capital we'll be using to achieve that cost? So one thing actually to remember before we start this problem is the cost function. Okay, in order to write that out, we'll be using this function a lot throughout the course, so it's very important for us to remember this and have a refresher. So cost is defined as the amount of the amount of labor that you'll be using and the price of that, and the amount of capital that you'll be using and the price of that. So that really is the cost function, right? And here it's 40L plus 10K, right? $40 for labor and $10 for capital. So how to write that in an equation? How do you write this in an equation? Oopsies. Okay, basically what we're trying to do is minimize our cost, right? Given that we have labor and capital as our coefficient, as our variables, sorry. And our cost function here, again, like I said, is 40L plus 10K. That's all we have to write. So minimize our cost given the L and K such that, so we write this ST, such that we have 1,000 is equal to L to the 1/2 and K to the 1/2. This is our cost minimization kind of problem written out in equations. So one thing that always remember here, when a cost minimization problem, we have our constraint right here, okay? And we have our objective. This is our goal, right? This is what we want to find out. This is what we want to work on. So constraint and our objective, right? So what I'll do now is, to proceed with this problem, I know my handy dandy formula here, MPL over MPK is equal to W over R. And right now, as of right now, we actually have every number to use to proceed with this problem. We have everything we need, okay? MPL over MPK, we can find this out from our, from our production function right over here, right? We can find this value from here just by taking the partial derivative. We can find our W over R, which is already given to us in a way, right? It's a $10 and the $40. But to really know this, we have to kind of use our cost function. So we can find W over R from cost, we can find this from our production function, and then we're done. Then we can find our L to K ratio and then actually solve for L and K and then solve for our cost. So let's proceed. We know here, I'll use blue. We know here that MPL over MPK. So let's focus on our production function, right? What is the derivative with respect to L over, with respect to L to the 1/2 and K to the 1/2? If you really just take the derivative, you should at the end of this get K over L. Here, W over R, we know that the partial derivative with respect to L and K, it should be equal to 40 over 10, right? Now, let's do cross multiplication, and we should get 10K is equal to 40L. And we should be left with K is equal to 4L. This is our ratio. This is very important for us to go back and plug this into our constraint. Our goal here is to always be able to plug this into our constraint, right? We want to make sure the 1,000 stays the same, and we have a ratio for K versus L that we can always plug into our constraint. All right, now you're probably asking, how did you get this? How did you get the K over L? Let me just do this on the side. Now, MPL here, again, we're looking at our constraint. MPL, the the partial derivative with respect to L is really just 1/2 L to the negative 1/2, and the K to the 1/2 stays the same. It's MPL. Okay. Now, similarly, MPK would be 1/2. Again, you bring down to 1/2. L to the 1/2 stays the same, and then K to the negative 1/2. Now we can start crossing things out, right? 1/2 cancels with 1/2. Negative 1/2 plus, negative 1/2 minus 1/2 actually tells us that L will be in the bottom, right? So it'll be L to the 1. And then this will actually end up going to the top, right? 1/2 plus 1/2. K will go to the top. So that, whenever you take the partial derivative, this is like the basic ones. It'll always be K over L here when you're taking the partial. So that's how I got the K over L. Okay, so moving forward, we have a nice little equation here. Let's bring this down. So now what we have to do, again, plug this back into our constraint, right? This is very easy. It gets very easy after this. Plugging it back into our constraint, we have, again, 1,000. This is confusing me. 1,000 is equal to K. We already know what K is. So let's just write this out, actually. Another way of writing L to the 1/2 is just square root of L, and this is our K, right? So now, we already know what K is, so let's just plug it back in. 1,000 is equal to L to the square root of L over K is equal to 4L, so might as well just do this, right? Again, 1,000 is equal to multiply whatever is on the inside. It should be 4L squared, and luckily this gives us a really clear number, which is just 2L. Square root of 4L squared is just 2L. L is 500 here. Perfect. We have a part of our answer. Now, once we have 500, this just gets easier. Plug this back over here. Sorry, we don't have to plug this here. We can also just plug it right over here. This is our equation that we plug it back into, and we should get K is equal to 4L, right? K is equal to 4 times 500, and, oh, sorry, this should be 2,000. So that's a part of our answer. Finally, all we have to do, when we have our L and K, all we have to do is plug it back into our cost function, right? Because we already have W and R, we already have K and L. All we have to do is, here's our cost, right? WL plus RK. Now we know that W is 40 times L is now 500 plus we have 10 times 2,000. That should be equal to 40,000. That's your answer for part A. Now, suppose that the desired Q doubles. Now we want Q has to be equal to 2,000. Okay, let's write that out here. Maybe I can fit it in the space. So we have to know that Q is equal to 2,000. And again, our production function, we're going to use, and we know that the K here is 2,000 again. So we'll just plug it in, right? We know K is 2,000. We don't have a given equation anymore. We don't have this little equation right now. We just know that K is 2,000. So why not just plug this in, right? Now we have 2,000 is equal to L times, well, that's pretty easy, right? All we have to do is square both sides to get a nice answer. So 2,000 squared is equal to 2,000 L. So now we know if we just solve this, we should get 2,000 times 2,000 is equal to 2,000 squared. So we know that given this, L has to be equal to, oops, sorry, I keep doing a dollar sign. L has to be equal to 2,000. We need 2,000 units of labor to have this work. And we already know that K is 2,000. Again, we're always solving for cost. So cost will be, again, $40 times 2,000 plus $10 plus 2,000. And that should give us 100,000. All right, so that's, oopsies, that's our answer for part B. This is our answer for part A. All right, so suppose that the firm is actually free to vary K while producing Q is equal to 2,000. What will happen to our cost? Whenever we see, suppose that our firm is free to vary K, that just should give us a alarm that this is a long run problem, right? What happens in the long run, right? You can vary it in any way you want. They're asking what happens in the long run, really, right? But the good thing is, in the long run, the MPL over MPK is equal to W over R still holds in the long run. Okay, so now we can still use the K is equal to 4L in this equation. And now it'll make everything very, very easy again, right? We can still use that. So now let's go back. We know that Q is equal to 2000 here. So again, let's equate 2000 is equal to L and again 4K, or 4L, sorry. How did I get the 4L? Because I know K is still equal to 4L in the long run. Nothing really changes, but you'll see something else that changes, okay? In the long run, okay, and then 2000, we do it very similarly like we did before, is equal to 4L squared, and then we should get L is equal to 1000 here. And K should, again, because we know that K is equal to 4 times L, K is equal to 4 times, 1000, should be 4000. K is 4,000, L is 1,000. Notice a difference here when we're calculating our cost, right? Our cost is, again, going to be $40 times 1,000 now, plus $10 times 4,000 here, and that should be equal to 80,000. Notice that in the beginning, here, in this problem, we had a cost of 100,000, but in this problem, we had a cost of 80,000. What changed, right? In the short run, here, we have a higher cost. In the long run, we have a lower cost. One thing to remember is that in the long run, the cost should decrease because, there's just a higher efficiency due to the production process. There should be a decrease in the prices in the long run because of this. So I really hope that this helps. There's a lot of this is to do with a lot of practice, right? A lot of plugging it back into the constraint, making sure that you have the values for your K and L and then cost, K and L and cost. It's very repetitive. If you just have a lot of just intuition as to how this works, it should be helpful. So thank you for watching.